Hello friends, I Dr. Mohan L. Verma welcome you all in this course on Fundamental of Engineering Physics, and today I am going to cover a topic that reflection, refraction, interference and the diffraction of light. And the outlines of this course today in this lecture I am going to cover that classification of optics, the reflection of light and then the refraction of light and various observation, interference, an introduction and its application, diffraction of light at a glance, and then difference between interference and diffraction, and the importance of ray and wave optics in a real world. So, the objective of this lecture is to introduce ray and wave optics of light, to impart knowledge on interference and refraction of light, to introduce interference and diffraction phenomena of light, to give comparative analysis of ray and wave optics, and to discuss about the applications, various phenomena concerned with the light. After attending this lecture, you will be enabled to understand the basic concepts of reflection, refraction, interference and diffraction phenomena, and you will be able to apply reflection, refraction, interference and diffraction in daily life events, and you will learn, you will be able to learn some fundamental mathematical formula to solve properties concerned with ray and wave optics. So, the classification of optics. So, optics is actually the study of light and its various properties. So, on the basis of different properties like that the transmission of light in a straight line and its color, and that different phenomena like reflection, refraction, interference, diffraction, total internal reflection type things. This optics is actually classified in the several parts. Actually, this light is very mystical. Yes, its behavior is very fascinating. It is difficult to comprehend light as a single entity. It can be classified as ray optics, wave optics, and in the beginning of that 20th century, one more optics is added, that is the quantum optics. The ray optics deals with light, it represents as a ray traveling in a straight line, and the wave optics this deals with the wave aspects of light and explain the phenomena like reflection, refraction, interference and diffraction, and then this the present scenario of that the properties of light, where we considered light as a photon, that the energy of the packet of energy, then that quantum or photonic aspects of light which one can study the quantum optics. So, the reflection of light, so this is actually the part of ray optics, and where we consider that light travels in form of ray, and especially that reflection is actually the bouncing back of light into the same medium when it encounters a reflecting surface, it is called the reflection. And that any polished surface that can reflect light, for example, that mirrors which are actually the silver coated at their back, this can reflect almost 90% of the light falling on them. The angle of incidence I, that is in the same side, and the angle of refraction R are measured with respect to the normal drawn to the surface at the point of incident of light, and that will be in the same side of that mirror or that reflecting surface. So, there is obviously, if there is reflection of light is we are considering, then obviously this will follow some specific law. So, according to the law of reflection, this is shown in this diagram, that incident ray and that refracted ray and a normal to the reflected surface, these are in the coplanar, that will be in the same plane. So, that will be not like that light is incident like this, and that the ray which is reflected in that will be in the again another plane. So, that will be on the same plane. And the second, the angle of incident I, it is equal to the angle of refraction R. This is one of the important law of reflection. So, always this is used in various devices, and the law of reflection, these are valid at each point for any reflecting surfaces. That reflecting surfaces will be flat, or that surface will be maybe that curved type surface, and that curved surface will be that concave or convex type surfaces. Then that image formation in plane mirrors. So, this is that schematic diagram of image formation. So, here that the image formed by a plane mirror, this is actually the virtual, erect and laterally inverted sidewise And what it means that when that will be when that reflection image is concerned, that that left hand side will be in the right hand side and right hand side will be in the left hand side in that in the image, and the size of the image that will be equal to the size of the object, and the image distance behind the mirror is equal to the object distance in front of the mirror. Means if you are standing in front of mirror about 1 meter distance, then that image will be obviously that will be 1 meter behind that mirror. And if an object is placed between two plane mirrors inclined at an angle of theta, then the number of image n that formed it is given in form of table. So, it depends on that value of theta, actually it is either even or odd, and that symmetric and unsymmetric means that the mirror is that angle is divided symmetrically or unsymmetrically. So, this is the formula for the total number of images formed. So, that the if that it is even, then in the symmetric form that number of images will be n is equivalent to 360 by theta minus 1, and in asymmetric form that n is equivalent to 360 by theta minus 1, and this is the case of the theta when it is even, and in the case of object odd, then the symmetric and unsymmetric form this formula is slightly changed, that is n is equivalent to 360 by theta minus 1 and n is equivalent to 360 by theta. So, that previous that was related to that plane mirror, but now let us think about that spherical mirror. So, what is about this spherical mirror? This spherical surface is actually the part that cut from the hollow sphere, and that spherical mirrors are generally constructed using this glass. One surface of this glass is silvered, that surface may be that concave surface or convex surface, and that reflection take place at the other surface which is polished. If the polished surface of the mirror is convex, then that mirror is known as convex mirror, and if that polished surface is in concave side, then that mirror is known as concave type mirror. And this is that schematic diagram for that two types of mirror, that convex mirror as well as that convex mirror and concave mirror. So, that inner surface in the case of that concave mirror, that inner surface is that reflecting surface, and in case of that convex mirror, that outer surface that is actually that reflecting surface. Some parameters or some terminology used in this spherical type mirrors. There is that center of curvature, the radius of curvature, pole, principal axis. Actually, that center of curvature is the center of sphere of that sphere, which the mirror is actually the part. It is called the center of curvature, and it is represented by C. And then the radius of curvature, obviously that radius is actually the distance from the center to that boundary of that sphere. So, the radius of the sphere of which mirror is actually the form, it is called that radius of curvature R. And the pole, the middle point on the spherical surface of the mirror or that geometrical center of the mirror, this is called pole, and it is represented by capital P. And that principal axis, this is actually the line joining the pole P and the center of curvature C. Some more is terminology like the focal point, this light rays travel parallel and center to parallel to the principal axis and incident on the spherical mirror, and converge at a point for the concave mirror, or it looks like it is a diverge from a point for the convex mirror, and that is known as that focal point, and it is represented by capital F. And the focal length, that distance between that pole P, which is actually that geometrical center of that mirror, and that focal point F, it is called that focal length F. And then the focal plane, the plane through the focus and perpendicular to the principal axis, this is called the focal plane of the mirror. This is that interpretation of a representation of all these points, that focal point F, that pole P, center of curvature C, that focal length F, and that radius of curvature R, and this is for both convex and concave mirrors. So, that the image formation in a spherical mirror, so that the law of image formation of that spherical mirror, it is much different from that plane mirror, and to locate an image point on a minimum of image point. These are that some schematic diagram, and out of these 4 diagrams at least 2 should be followed by, must be followed by that image. So, minimum 2 of this ray must meet at that point, and we can use at least any 2 of these following 4 rays. So, that then the first ray what is observing. So, that ray, it is passing parallel, it is moving parallel to the principal axis. After reflection it cross that focal point, and then the second point, when that ray it is passing through that that focal point, it will, after reflection, it will move parallel to that principal axis. And third, when that ray it is passing from the center of curvature, then this will come back with the same path. And that the third one, that is, if that ray it's incident on that focal point, then it will follow that law of reflection. So, this will move with the same angle in the same direction. And some conventional rule we have that if that generally in the conventional rule of that formation of image, actually that light always incident from the left hand side, and all the measurement taking from taking towards the direction of that that incident of light, that is always positive. And that the next one, that after reflection, if it is following opposite to that direction of incident of that light, that will be obviously measured in the negative. And that all the measurement taking in the upside of that principal axis, that will be positive, and in the bottom side that will be negative. So, depending on this we can solve a different mathematical calculation, and this is that one formula which is known as that mirrored formula. It is used to solve numerical problems, and by referring some good textbook, one can get different numerical problems related to this formula. So, here this formula is 1 upon v plus 1 upon u is equivalent to 1 upon f, where this v, it is actually the distance of the image from that pole, and that u, this is that distance of that object from the pole, and that f, small f, this is actually the focal length, and obviously this distance is also measured from that pole point. So, the second phenomena, this also belongs to that ray optics, and this is known as that refraction. So, that refraction is passing of light from one optical medium to another optical medium through a boundary, and in refraction the angle of incident I and the angle of refraction R, these are measured with respect to the normal drawn to the surface at the point of incident of light, and this is that one of the schematic diagram of that refraction. So, here we have two mediums, one will be obviously rare medium and second will be the denser medium, and obviously these two mediums will be transparent medium. And the law of refraction of light. So, according to this law of refraction, the incident ray in the first medium and the refracted ray, obviously that will be in the second medium, and the normal drawn that on that the surface, that boundary to the refracting surface, and these are on the, obviously that will be on coplanar. This is similar to that the law of reflection. There also all that these 3 lines are coplanar, and here also these 3 lines are coplanar. Second, the ratio of sine of angle of incident I. So, here some trigonometry is involved, and in the first medium to the sine of the angle of refraction, that is in the second medium, these are equal to the ratio of that refractive index, and it is represented as N2 of N2, and that refractive index of that the first medium, that is N1. So, that sine I upon sine R, it is equivalent to N2 by N1. So, this is actually known as Snell's law also. So, somewhere it is represented as N21. So, this N21 is equivalent to N2 by N1. The angle between the direction of incident ray and the refraction ray, this is called as the angle of deviation, and this is obviously due to that refraction. And when light travels from rare medium to denser medium, then that this angle of deviation, this reduces, and that d is equivalent to I minus R. So, obviously that I is measured in that rare medium and R is measured in the denser medium. So, this deviation, this D is equivalent to I minus R, and that vice versa. When this light passes from denser medium to rare medium, then this will be equal to that D is equivalent to R minus I, because this R will be greater with compared to that angle of incident. So, the relative refractive index. So, that comparison of that refractive index with these two medium, that is obviously that relative refractive index. So, the term N2 by N1 is called relative refractive index, and that is with compared to second medium with respect to the first medium, and this is denoted by N21, and this concept of this relative refractive index, this gives rise to other useful relations like that. So, this N12 means that refractive index of second medium with respect to 1, that is equivalent to 1 upon N21, or N1 by N2 it is equivalent to 1 upon N2 by N1, and there we can use that chain rule like that. So, in the chain rule that N32 it is equivalent to N31 multiplied by N12, or that N3 by 2 or N3 upon N2 it is equivalent to N3 by N1 multiplied by N1 by N2. So, some common observation in daily life because of this refractive index or that refraction phenomena. So, one is that apparent depth, it is a common observation that the bottom of a tank this filled with water, it appears to be raised when seen from air medium above, and this is that schematic diagram, and that is because of that the deviation of ray when it passes from one medium to another medium, and there are two schematic diagram observed in two different direction when we observe it vertically to that surface of water and with an angle from that surface of water. And one more observation, that is the atmospheric refraction. So, due to the refraction of light through different layers of atmosphere, we know that atmosphere having different density and which varies in the refractive index, and the path of light deviates continuously when it passes through one layer to another layer, and this sun is visible little before the actual sunrise and also until a little after the actual sunset, and this is due to the refraction of light through this atmosphere. And second, one of the important observation obviously in astrophysics, that is the twinkling of a star. So, actually the star do not twinkle, and they appear like twinkling because of the movement of atmospheric layers with various refractive index, which is clearly seen in the night sky, and that star which is just on top of our head, that the twinkling rate is very less with compared to that star which is parallel to our eyes, and that is because of that different column of atmosphere through which that light ray is passing. Now, I am including here two more phenomena that is related to wave optics, where we are considering that wave nature of light. One is that interference. So, the phenomena of superposition of two light waves which produce increase in intensity at some points and decrease in intensity in some other point, this is called as that interference of light, and that pattern is known as interference pattern. And when two waves simultaneously pass through a particle in a medium, that resultant displacement of that particle is the vector addition of displacement due to the individual wave, and the resultant displacement will be maximum or minimum. This depends upon the phase difference between these two superimposing waves. And these waves which are actually being superimposed have different properties, like these are parallel, similar same frequency, same velocity, similar amplitude, and these are that schematic diagram of this. So, this is actually known as the law of superposition. So, these are that two waves, and these two waves have different amplitude A1 and A2, and there is one phase difference of phi. Then we can interpret these waves as y1 is equivalent to A1 sin omega t and y2 is equivalent to A2 sin omega t plus phi, and when we use that superimposition principle, then y is equivalent to y1 plus y2. And by using some simple trigonometrical calculation, we will have that the summation, that sum of these two waves as y is equivalent to a sin omega t plus theta, where this a, that capital A, this is that resultant amplitude, and that is formulated as equal to root of a1 square plus a2 square plus 2 a1 a2 cos theta, and that theta that is equivalent to tan inverse a2 sin phi upon a1 plus a2 cos phi. So, if we want to have this amplitude maximum, because this amplitude is concerned with that intensity of light, and in the case of that interference we are thinking about that distribution of high intense point and low intense point. So, where that intensity will be high or that low, that depends on that amplitude that is being maximum or minimum respectively. So, in order to get that maximum amplitude, this actually depends on that phi, the angle between these that phase difference between these two waves. So, if this phi that is equivalent to 0 plus minus 2 pi plus minus 4 pi, then by using that simple mathematics, that resultant amplitude that will be a maximum, it is equivalent to a1 plus a2, or that in case of that minima, when this phi is equivalent to plus minus pi plus minus 3 pi, this odd multiple of that pi, then this a minimum it is equivalent to a1 minus a2, and that intensity, since that intensity is proportional to a square. So, that intensity I is equivalent to I1 plus I2 plus 2 under root of I1 I2 and cos phi. So, if the phase difference is phi, it is equivalent to 0 or even multiple of that pi, then this corresponds to condition for maximum intensity, and here this I max it is proportional to a1 plus a2 square, or this I max is equivalent to I1 plus I2 plus 2 root of I1 I2. And if we take that specific condition, when these two waves have same amplitude, then this I maxima that will be 4a square, that is actually equivalent to 4 times the intensity of the first beam. And that the first case, that is known as constructive interference. In the second case, where that intensity it is minimum, and this is possible when this phi is equivalent to plus minus pi, or that odd multiple of pi, and this condition, this will actually gives that minimum intensity of light, and that interference concern is known as a destructive interference. And this resultant intensity that is equivalent to I minima, it is proportional to a1 minus a2, that the whole square of this, and I minima in terms of intensity of individual light, that is equivalent to I1 plus I2 minus 2 root of I1 I2. And in the case of a spatial condition, that is when we consider that A1 is equivalent to A2 is equivalent to A, then that the ideal intensity, the minimum intensity must be 0. In experimental phenomena, in place of that phase difference, we consider that path difference. So, what is actually that relation between this phase difference and path difference? So, phase is actually the angular position of variation with the waves in progression, and whereas in there is a relation between this phase and phase of that vibration, and the path is actually that path travelled by the wave, and in the path of this wave, one wavelength lambda, it is actually corresponding to the in terms of that phase, that is equivalent to 2 pi. So, the relation between this path difference delta and that phase difference phi, it can be calculated as equivalent to delta is equivalent to lambda upon 2 pi multiplied by phi, or in terms of that phi is equivalent to 2 pi by lambda multiplied by delta. So, this is that useful relation people generally use when they consider that experimental phenomena concerned with this interference. So, this is a schematic diagram of that path and the phase difference of wave. Now, as just I discussed about that different condition for the interference, that amplitude is similar, it is moving parallel, velocity is same, frequency is identical. One term is used in interference, that is the coherency or coherent sources. So, this is essential condition for the interference phenomena, and these the two light source, these are said to be coherent if they produces wave which have same phase or the constant phase difference. So, if we are considering a single wave, means its phase must be constant, or if we are considering two waves, then the phase difference must be constant with the same frequency or wavelength, and obviously that wavelength is same, is monochromatic, and same waveform, and preferably if the amplitude is same, then this is good. So, this type of waves are known as coherent waves, and in order to obtain this coherent light waves, we generally have three techniques. One is that wavefront diffusion or diffusion of wavefront, and generally this is used in Young's bisect experiment, and second that the diffusion of amplitude. So, in that Michelson's experiment or Newton's ring experiment, we use this phenomena, and that source and images. So, actually that image is created, and that image is considered equal to that source, and this is one phenomena used in Fresnel biprism. So, this dazzling color, and these are exhibited by the thin film of oil sprayed on the surface of the water and also on the soap bubble, and this is one of the phenomena which is mainly due to that interference, and we observed in our daily life. And the color actually depends on the thickness of the film. So, there is one separate topic related to that, a thin film, where that interference phenomena is occurred, and in that the thin film have that different refractive index, and that it depends on that angle of incident of light and that reflection of light on that surface. So, this is that diagram of that dazzling color, and that beautiful color is observed, but that first one is that petrol sprayed over the road, and second one is that soap bubble, and next one is that schematic diagram of that. Now, that the luster phenomena, that is also related to that wave optics. So, this is that the phenomena which is concerned with the wave properties of light. So, diffraction is actually the characteristic of all waves, including sound waves, and that this is the bending of waves around the sharp edge into the geometrically shadowed region, and that diffraction is prominent only when the size of obstacle at that sharp edge it is comparable with the wavelength of light. So, this is that essential condition for the diffraction. So, the wavelength of that wave that must be in the order of the size of that slit or that side of sharp edge, and this is the reason why sound waves get diffracted prominently by obstacles like door, windows, and buildings, and this is the reason that is why if some person is standing behind that wall, we can hear its sound because of diffraction of sound on that sharp edge of that door or that wall, but we cannot see that person just talking behind that wall, because that light's wavelength is not comparable to that size of that wall. So, the diffraction is light is more pronounced when the obstacle size is in the order of wavelength of light. So, diffraction is classified into two parts, that experimental purpose. So, the Fresnel and Fraunhofer diffraction, and this is actually based on type of wave front which undergoes a diffraction, and it could be classified in Fresnel and Fraunhofer diffraction. So, here one term is used is that wave front. This is actually the front of wave, and generally in wave theory it is considered that this light actually travels in a straight line in form of wave front, and this wave front actually it is classified into three parts depending on the shape of that light source. And this is the Fresnel diffraction. So, here that spherical or cylindrical wave front undergoes this Fresnel diffraction, and this light wave is actually formed at a source which is at the finite distance, and also one convex lens it is needed to use or that locate that particular light source at a specific distance, and it is difficult to observe and analysis. So, this as far as that experimental is concerned, this Fresnel diffraction observation it is very difficult. The second type of that diffraction, that is the Fraunhofer diffraction, and this is because of that plane wave front undergoes diffraction, and in order to get that plane wave front, obviously the condition will be that light source must be at infinite point, and so experimentally if we want to have this parallel light source, then we put one convex lens in just in front of that light source at that finite distance, and we get that parallel light source if that light source is placed at the focal point of first focal point of that convex lens, and so this it is easy to observe and analysis, and obviously that for the observation we also use another convex lens because we have to observe that that diffracted point at the finite distance. So, what is actually the difference between interference and diffraction phenomena? So, we have that interference phenomena, there we need two parallel beams and in the diffraction phenomena one single beam is required, and that there must be one sharp obstacle or sharp edge, and that will be diffracted. So, in interference fringe especially, it is equally spaced bright and dark fringes. So, all the intensity of all the bright fringes and the dark fringes that will be identical, and then the large number of fringes can be obtained. So, this is actually the difference between that fringes. So, all the fringes are having equal intensity as well as equidistance, and whereas in the case of that diffraction, so that central bright fringe is double the size of the other fringes, and the intensity falls rapidly for higher order. So, as that the central dark fringes will have highest intensity, and as we move from that dark fringes to central fringe to other fringes, then intensity of that fringes that will decreasing, and that least number of fringes are obtained. Only 3 first order, second order, third order diffraction pattern can be observed experimentally. So, this is that diffraction in single slit schematic diagram, and we use generally that the formula that is known as the diffraction formula 2d sin theta is equivalent to n lambda, and it can be calculated using this. And so, here we will have this is single slit experiment, and we will have double slit experiment also, and experimentally we generally use n slit experiment, and that n slit experiment is actually known as the grating, diffraction grating. So, that grating is actually a plain sheet of transparent material on which that opaque ruling are made, and by using that sharp edge of a diamond, and a modern commercial grating, this contains about 6000 lines per centimeter, and the transparent space between two ruling acts as slit of width A, and the rulings acts as obstacle having a obviously definite width B, and this that A plus B, this is represented by E, and this is known as a grating element. So, in that formula 2d sin theta 2d sin theta is equivalent to n lambda, that D or 2d, it is considered replaced by this grating element E in experiment. So, this is that n slit experiment, or that diffraction grating experiment. So, A plus B sin theta is equivalent to m lambda, it is used, and m is actually that order of diffraction. We can that in general observation, a compact disc CD, this always appears colorful on the read or writable side, which looks shining, and there are many narrow circular tracks with width comparable to the wavelength of visible light. Hence, the diffraction takes place after the reflection of incident white light to give colorful appearance. So, that diffraction phenomena we can observe on this compact disc CD. So, as a summary, we can have that we have 3 category of that optics, that is that ray optics, wave optics, and that quantum optics. So, in the quantum optics, this is that recent techniques, and here in this particular topic we considered only that ray optics and wave optics, and in the ray optics we have considered 2 phenomena. One is a reflection, the second one is a refraction. So, reflection, this is one phenomena which actually one light when incident on that reflecting surface, it travel back to the same side, and it follows that law of reflection. And then the case of refraction, when it light travels from one medium to another medium, then its path changes from its original medium, and there is Snell's law, where this sin I by sin R, it is equivalent to that refractive index of medium with the medium first medium with compared to the second medium. And then we further considered 2 more phenomena, that is concerned with that wave theory of light, the wave properties of light, wave optics, and that was that interference. So, this interference is actually the superimposition of 2 waves having distinct properties, like these are parallel with same frequency, same wavelength, coherent, and the similar amplitude. Then it creates one interference fringe where there is alternate dark and bright light points are there, and we have classified this depending on that intensity of these points, that constructive interference and destructive interference. And then the last the phenomena, that is that diffraction, this is the bending of light when that light passes from sharp edge or that obstacle, and the condition that is required to for the diffraction is the size of that obstacle or slit that must be in the order of view, and this is that phenomena which can be observed in sound as well as the light. Anyway, so happy learning and thank you all.